parts and how the blender works, what do you notice? So first is that there is a mechanism uh, which results in some desired motion within the application. So you have a DC motor, you have a central shaft on which there is a worm which rotates nylon worm wheels which are supported on some bushing, and the nylon worm wheels in turn rotate the blender blades. That is the mechanism which is involved. And there are a bunch of mechanical parts. So you have the shaft, bearings, worm screw, the fan, bushings. These are the mechanical components. Anytime you design a machine, your first objective is to come up with design for parts which will achieve the desired motion. Okay, that is the first or the primary objective, to get some desired output or desired motion. As a part of this, you will think of some mechanism parts which will finally give you that motion. Once the primary objective is met, the next objective is to ensure that this system works in a reliable manner for a long period of time, meaning that each time you switch on the system, it should not break down and it should continue to operate in the same manner, in a consistent manner for a pretty long period of time. Let's say hundreds of thousands of operations of the machine. That is where the failure analysis or the design analysis comes into picture. Once you have come up with the parts which are going to be involved in your system, you need to look at the forces and the stresses they are going to be subjected to, and you need to ensure that none of them will fail. Now, in this context, it is important to know what are the different ways in which parts can fail. And this particular lecture is going to be about that. Please keep yourself on mute unless you are answering a question. Okay. I see somebody is unmuted and okay, just a second. All right. So today what we are going to look at is I'll be talking about a bunch of case studies. I'll be telling you the background story of what was the failure which was observed within the system, and you will have to figure out as to what went wrong. Okay. And through this exercise, you are going to learn as to okay, what are the different ways in which failure can happen. Okay. So let's move on. So today's thing is basically to identify the failure mechanisms in the following case studies. Fine. The story for this particular machine goes like this, that around 10 years back, Indian Railways came to us with a problem. The problem they were facing was that during the train was that the railway wheels were running hot due to tread braking. So in Indian Railways, whenever the train has to be braked, in most of the cases, the brake block presses against the wheel tread surface, the outer surface which normally comes into contact with the rail. On that particular surface, brake load is applied. Loads are quite high. The brake load is typically of the order of about 2-ton force, okay, or 20 kilonewtons. So brake load is applied. So whatever is the kinetic energy of the train, which would be massive, considering its weight and the speed at which it goes, all that kinetic energy would be dissipated as heat during the braking process. And because the brake is being applied directly on the wheel, you have heat being generated, and the wheels, over a period of time, they become hot. Now, they have been doing whatever they have been doing for the last 60 to 80 years, but during 2005 to 2010, they suddenly started seeing warping of the wheels. The wheel shape was changing, and the gap between the wheels, which is called wheel gauge, was increasing. Normally, the gauge means for the broad gauge, it is somewhere around 1690. We have broad gauge tracks. The tolerance on this gauge is very small. It should not decrease by more than 0.5 mm, and it should not increase by more than 3 mm. But in quite a few, particularly locomotives, they were seeing that the gap between the wheels is increasing. They wanted us to study the problem and figure out what is the root cause. Now, we had thought wrongly at that time that the material was undergoing creep deformation. So, you must all have heard about elastic deformation, plastic deformation. Now, creep, I'm not sure how many of you have heard. Can you raise your hand in Teams if in case you have heard about creep deformation before? Okay, so some of you have heard, many of you have not heard. Okay, so creep deformation is something which happens in materials. It is permanent deformation which occurs in materials when they are subjected to stresses for a prolonged period of time at elevated temperatures. For metals, the elevated temperature means you are looking at temperatures above 0.3 or 0.35 times melting point in Kelvin. So we had wrongly presumed that it is because of creep, and we had proposed to do extensive creep study of railway wheel steel. So for now the and we wanted to do it under combined loadings. We wanted to subject the material to both tension as well as torsion. So therefore we thought we should come up with this tension torsion creep setup. Now so all right. Now the machines which were available in the market, first thing we could not find any commercial machines, and creep machines were mostly commercially available machines were run on hydraulic systems and were very expensive. They were costing more than a crore, and creep experiments materials have to be subjected to stresses for in some cases for several days together. If you use a hydraulic system, the hydraulic power pack must be switched on all the time. And in India, conducting an experiment over several days without interruption is a very big challenge because of power cuts and other things that we face. And also that money of 1 crore and above was too costly for us. So we thought we'll make something ourselves. And we thought that instead of using hydraulics, let's just use dead weight to somehow apply the load that we are interested in. So I came up with a design, and this was my first ever designed and built machine. So, okay, so the mechanism goes as follows. You have a guide rail. Okay, so this long bar that you see, this is a guide rail, and on that you have rail blocks. So the green colored thing that you see, this is the rail block. Okay, now and okay, the rail block can move freely along the rail. Okay, sorry, along the rail. Now what we had done was we had taken 3 rail blocks. The middle rail block is free to translate along the rail, and the outer 2 rail blocks were held fixed to the rail. So we had made some arrangement. Okay, so we had we had used some plates, and basically we clamped the rail block to some plates, and those plates were in turn clamped to the rail. So this way we had arrested the motion of the two outer rail blocks. Okay, and then uh, is it okay if I speak like this, or you need me to write on the screen?
No, sir, it's okay, I think.
Okay, fine. So this middle rail block can slide freely along the rail. The outer two rail blocks are fixed. And then we have made these columns. Okay, the columns are rigidly attached to this rail box. Let's call this a column. Okay, so you have these structures over here. Now, in order to apply tension, what we had done was, so we have a tubular specimen. Okay, so what you see over here in the middle, where the laser pointer is there right now, that is the specimen which we want to subject the load to and whose deformation we will monitor. Okay, now this specimen is attached to this particular vertical column which can freely translate, and then inside this block over here we have a taper roller bearing. Okay, we have a taper roller bearing, and the inner raceway of the taper roller bearing is free to rotate and is attached to this particular lead screw, ball screw. Okay, so this is a ball screw over here. What you see, you can see the threading. So the inner raceway of the taper roller bearing is attached to the ball screw, and the ball nut is there over here, and it is fixed to this vertical column. So now as I rotate this pulley disc, okay, which is once again rigidly attached to the ball screw, what will happen? What sort of a motion will be generated? So the ball nut is fixed and the ball screw is being rotated, and the ball screw shaft is attached to the inner raceway of a taper roller bearing. Okay, so as I rotate this ball screw using the pulley, what kind of a motion will I generate for this particular column which is free to slide?
It will translate.
It will translate along this particular along the rail. Okay, so I use this mechanism over here in order to cause translation of this column along the rail. Okay, now the ball screw was,
Sir,
yeah,
so how is it causing translation?
well, for a screw, uh, as if you keep the nut fixed, as you rotate the screw will also translate along the axis of the nut.
No. So what's the role of that roller bearing?
Sorry, what is the role of the roller bearing? See, the ball screw is rotating, but the column is not rotating, right? Column can only translate. So you need some you need an element where, like, the inner raceway or the inner part is rotating and the outer part is fixed. So the column is attached to the fixed raceway, which is the outer raceway of the bearing.
Okay.
In a structure, whenever you have a rotating element, it must always be supported on a bearing so that it will allow the rotating part to rotate freely and be supported on the stationary part. That is the purpose of a bearing, actually. So, okay, so you use this ball screw for that, and the ball screw had a pitch of 5 millimeters, and the pulley had a diameter of 300 millimeters. Okay, now if I am using a weight, okay, which is hung around this particular pulley, for 1 mm movement of the weight, okay, 1 mm downward movement of the weight, what is the amount of translation that I would get? The pulley diameter is 300 millimeters. The pitch of the ball screw is 5 millimeters. So for 1 mm downward movement of the weight which is hung around the pulley, what will be the corresponding motion, linear motion achieved for the ball screw? So one rotation of the pulley will lead to uh, a movement equal to lead. This is a single start thread. Sorry, I didn't say that. So the lead will be equal to 5 millimeters. Okay. So pi d. So for pi d amount of movement of the mass, okay, you have a 5 mm movement over here. So what will be the ideal or the theoretical mechanical advantage you get in this application? It will be pi multiplied by 300 divided by 5. Okay, so you get a huge mechanical advantage in this particular system. So by applying a weight of 1 kg, how much force can you generate on this particular specimen in this arrangement? Neglect losses.
So about
How much? Okay, so it is roughly, let's say 3 into 300 is 900, 900 divided by 5. So you get 900 divided by 5. So you get 180. Okay, you get a means a theoretical mechanical advantage of around 180 in this application. So which means if you hang 1 kg mass on the pulley, you end up applying close to 180 to 200 kg force, or about 100 and about 1800 to 2000 newtons of force on the specimen. Okay, so this mechanism gives you a huge mechanical advantage. And in the same manner, if you have even 10 micron change in the length of the specimen, that will cause a downward motion of close to 1.8 millimeters for the mass. So in both ways it is a huge positive for this particular creep setup. So in any case, so we use this mechanism to apply tension or compression. So if you rotate the pulley in one direction, you get tension. If you rotate the pulley in the other direction, you get compression. So we can use this for tension compression system. Now, in order to apply torsion, what we had done was, on this side, the specimen can translate, but it cannot rotate. On this side, the specimen translation is fixed, but it is free to rotate. Okay, so over here, the specimen is mounted on a bearing, okay, which will allow it to freely rotate. So through this pulley wheel and the weight being applied through the pulley, you can apply torsion. So using this setup, we had thought we will apply tension torsion, and we had designed the columns, the ball screw, everything in a manner that nothing will undergo plastic yielding, even if you apply 3-ton force on the specimen, meaning about 30 kilonewtons, and about 100 newton meters of torque. Okay, even under this combined loading, with means we designed such that none of the parts would experience plastic yielding. The stress was well below the yield strength of the material. Okay, but when we use this setup for the first time, we saw a major flaw. Means we missed something completely during the design process, and we had to modify the setup in a big way. Not a big way, we had to modify the setup so to make it work later on. So take a minute, think about it. What do you think we missed? We missed something fundamental because of which we could not apply like tension, a simple tension torsion on the specimen. A much more complex loading was appearing on the specimen. So what do you think we missed in the design process?
The bending load.
So
Uh,
the
yeah,
guide rail was bending.
yeah. Who is this?
Yashashvi.
Yeah. So that's that's a correct answer. So what we had missed? Okay, can you explain your answer? You are correct. Explain means.
Uh, so like it's getting vertical support from the two ends.
Uh-huh.
So the forces will be balanced in that direction, but the weight in the center will bring it down. Now, it's sort of that problem in which if a
No, no,
thread
no, no.
chain
Dead
is
weight,
hanging.
dead weight doesn't hamper it. Dead weight is very little. Nothing will happen because of dead weight. Okay, so I thought you got the answer, but that's not the answer.
So mainly due to the moment, due to the dead weight, it is
Sir,
causing the.
the tension.
Again, dead weight is very little. These things are not that heavy that they are causing any huge deformation anywhere.
Sir,
Yeah.
maybe a part of tension and torsion that we are applying through this whole process get transmitted to this rail due to the clamps that we have created.
Again, tension will not do
Sorry,
any harm.
torsion.
Torsion, it's not really getting transmitted. It does get transmitted, but torsion was not the problem. This beam has got quite a bit of polar moment of inertia. It won't really
Sir,
twist the beam.
when we apply compression and let's say that the specimen reduces its length by some amount,
No, no.
then
Remember that for creep, the steel specimen, the change in shape is minuscule. You can hardly
but
notice.
but sir, if we have to explain bending, then we can say that since there are two supports which are fixed on the rail, so because we are reducing the length by applying the compression or tension weight, we are increasing, so that will cause this rail to bend because it is fixed on two places, and in between of that we are changing the length to apply the
Mm,
load.
you guys are answering. You're somewhere close, but not exact. Anyone else would like to take a shot? See, this has got to do with the loading that we are applying. It's a large load. Okay, 3 ton is a lot of load. It is equal to nearly something like two Maruti Desires. Okay, 2 to 3 Maruti Desires. That much amount of force we are applying on the specimen. That force indirectly causes problems. Okay, so the deal is this: we were always focusing on failure from permanent deformation, stresses being very high, and all that. We didn't really think too much about the elastic deformations which are going to happen in this problem. So, what was the issue? The issue was that when we are applying tension torsion on this vertical column over here, we are basically generating a force of 3 tons, okay, or 30 kilonewton force. Now, this 30 kilonewton force is generating a moment of 30 kilonewtons multiplied by about zero point 0.2 meters, okay, which was a huge amount of moment. 6,000 Newton meters of moment was getting generated on the rail. Bending moment was getting generated on the rail at this particular point. And because the supports were quite far apart, this was resulting in bending of the rail like this. Okay, this was a very significant amount of bending deformation was being obtained for the rail. Now, how do I fix this setup? How do I change this setup to sort of fix the problem? I don't want to go about redesigning my whole machine. I just want to make 1 2 small changes so that this will work. So what should I
So
do?
the screw is
We
in
can
the first support or in the middle support.
So what we had done was we need to increase the bending moment of inertia of this rail by a huge amount. Okay. So what we had done was we had taken a very thick block of steel and which was continuous from this table. Okay, so then what happens is that the bending moment of inertia will be combined bending moment of inertia for the rail, for the steel block we put, and the table. Once we did that, this was working fine. Okay, so the moral of the story is that do not always be concerned about the strength and failure from either breakage or permanent deformation. Also, always pay attention to the change in shape that can happen in your system because of the loadings. Okay, so elastic deflections are as important as any permanent shape change in the parts. Okay, that's the moral of the story here. Okay, let's move on to the second case study. Okay, now the second case study concerns chemical industries. So when you're going on highways, you must have noticed these large cylindrical columns uh, whenever you pass across some company which is related to petrochemicals. Okay, now in one such company, they had all these different columns. By the way, whenever you see a column like this, okay, um, how do you think something like this is made? Anybody would like to venture?
Uh, Small segments are made and they are welded together.
Okay, but this looks continuous.
Sheet
Uh,
metal is rolled and welded at a vertical.
But that would hardly have any strength if you are using only sheet metal. Think of car body or think of the body of a CNC machine. Do you think the strength is coming really from the sheet metal? How many of you have tried to like press your hand against the outer body of, let's say, a Maruti car? What kind of a strength does it have?
So it has a frame.
There is a frame. Very good. So, see, it's a little bit like human body. Means, what is the purpose of skin on human body? What is the purpose of skin on human body, or for that matter, any living organism?
It is a protective layer.
Uh, a little bit more detail. Protecting from what?
From corrosion
From
of from outside world.
exposure due to different types of pathogens and weather as well.
Yes. Does it protect you really from forces or from mechanical? What should I say? Does it really give you strength? The skin?
No, sir.
No,
No,
sir.
No, sir.
just isolating the inside from the outside. That's it. That's the only thing that it is doing. So, in the same manner, means what really give you the strength within the human body?
Bones.
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 The bones and the muscles. Okay, so the bones, the load basically gets transferred through the bones, and muscles, fine, help you align the bones in a manner. They help you give you motion that you want, help you sit in a certain posture or something. But basically, it is the bones which do all the load transfer. Now, in the same manner, no, so if you take a car, for example, you have an underlying frame on which you put all these body panels. You take a CNC machine, same story. You use beams to construct a structure and then you put these sheets all around it. Okay. In the same manner, over here also, on the inside, there would be a frame which is made out of beams. You can have them either welded together or bolted, riveted, one of the three, but you come up with a frame, and then on the frame you would wrap this particular structure to isolate the inside from the outside. You do not want rain, dust, rats, ants, birds. You don't want these things to go inside your container. You want your contents to be protected from the external elements. Okay. Now, in one such structure, within the process, condensation was supposed to take place. Okay. Now, fine, they built this whole thing, structured, looked fine before they started using it. But then, as soon as they used it, okay, in the first run itself, in the column where condensation was supposed to take place, there was this collapse of the structure. Okay, so you can see this kind of a thing had happened. Okay, why do you think the structure collapsed upon use? And in failure, one point you can always think about is, did the failure happen the first time it was used, or did it happen upon repeated use? So this is a very important point. So what do you think happened here?
Atmospheric pressure crushed it.
Atmospheric pressure is there on all the columns, no?
No,
Why?
but like it is being balanced inside the by the gases or something. When the
Okay.
condensation is taking place, the pressure inside is less, and the
Why would a pressure drop due to condensation?
There is a huge difference in the volume of, like, when the liquid condenses, the volume
Yeah,
ratio is very huge.
that's the right answer. Okay, whoever answered, good job. So condensation results in a massive drop in the specific volume of the material that you are dealing with. So there is a sudden drop in the pressure, because of which basically you have a situation where atmospheric pressure is compressing the structure from outside, but there is nothing to counter it from the inside. Okay, this is similar to what happens when a submarine goes inside an ocean. You must have heard in many movies, right? There are so many movies which involve submarines. They say that okay, I have dropped to 50 feet above, 50 feet from the water surface, 100 feet from the water surface, and they say that no, I cannot drop any further down. Why? Because basically you have this pressure of water which is sort of trying to collapse this submarine from the outside. Sorry.
मैकेनिकल डिपार्टमेंट का एक कोर्स है डिजाइन ऑफ मशीन एलिमेंट्स
So, all right. So over here, the drop in specific volume results in a drop in pressure, and this leads to, what is this failure mechanism called? This collapse has a specific name. Just like permanent deformation, we call it as plastic yielding for structures. There is a technical name which is associated with this collapse. What is it called? So,
Implosion?
what is it?
Is it an implosion? Like,
No, not an implosion. Implosion, you use the word when you have like breakup of a structure and these parts are falling inside. Like sometimes when you are using explosives and you collapse a building, but you don't want the broken parts to fly outside, you want them to fall inside. You call that as an implosion. This is not, there is no explosion or implosion over here. What is this? It is basically buckling. So whenever you have a structure, you apply compressive loads on the structure, and there is a failure of the structure due to this massive shape change. You call that as buckling. So over here you have buckling, and this is one of the modes of failure, particularly where compressive loads are involved. Okay. Okay. Let's move on to the next case study. See, any machine that you take, bearings play a super important role. Okay. And in your application, if your shafts can rotate at many speeds, at low speeds, high speeds, okay. And if you want very little friction for your rotation of your shaft, then you go with roller bearings, okay. So there are a bunch of different bearings which you can use. So you have journal bearings, okay. So you can either use some hydrodynamic effects, or you can use plain bushings, air bearings. There are a lot of other options, but by far roller bearings are by far the preferred way of providing rotating shafts within a system. Now when you have a bearing, broadly speaking, you have three elements in a bearing: inner raceway. So you have this ring like thing with a groove in which rollers sit. This is the inner raceway. Then you have rollers. Rollers can be either spherical, cylindrical, okay. They can be tapered cylindrical, or they can be spherical. Rolling elements can come in different shapes. And then you have outer raceway, where you have matching groove but on the outer side. So either the inner raceway is fixed and outer is rotating, or vice versa. Okay. Can you name one application where inner raceway is fixed and outer raceway is rotating? Or let me start with the easy
Sir,
one.
a,
Huh.
a BLDC motor, in that the outer part of the bearing is rotating and inside one is fixed.
Not always. BLDC hub motor. Okay.
Yes,
Sir,
sir.
In
feed,
a
feed
hub
this unit.
motor, the outer is rotating and inner is fixed. If you take BLDC motor, for example, in a geared system, in a regular, let's say something like a three-wheeler, okay. So in that particular case, outer is fixed and inner is rotating. But BLDC hub motor, the if you take any automobile wheel, for example, in that particular case, the inner raceway is not always. Sorry, my mistake. So if you take a fine, this hub motor thing is a good example. And also if you take freely rotating wheels, okay, in automobiles, cars, let's take modern day cars. These are all front driven, means front wheels are driven, rear wheels are freely rotating. So if you take a freely rotating wheel, then normally the inner raceway is fixed and outer raceway is rotating. It is attached to the wheel and is rotating. So anyhow, so you have these raceways: inner raceway, rollers, and outer raceway. Now, in one of the applications, a truck, what happened was that after some use of the truck, the wheel started to make a lot of noise in the bearing region. Okay. So they took out the bearing and then they noticed that there were these indentation marks. These are called indents. So you must have heard in all hardness tests you do indentation and then you measure the impression area. So these are such sort of indents were formed on the bearing surfaces. So what do you think happened? Like, what is the failure mechanism, and why such sort of indentations or impressions are bad, and what do you think caused these indentations? Let us
Sir, maybe,
start with what is this failure mechanism called.
sir, maybe due to excessive loading, the balls of the bearing cause the indentation.
So that is a possibility. So what is this failure mechanism called?
Plastic deformation.
Very good. So this is failure from plastic yielding of the material, okay, which is a fancy word for causing permanent shape change within the material. Anytime you see a change in shape happening due to indentations, or yeah, basically permanent shape change in the material, you have plastic yielding. So that is the failure mechanism over here. What do you think might have caused it? So you said excessive loading. Um, can means why did it not form a continuous groove? Why do you think it formed this ball marks? After all, bearing raceways rotate, right? Rollers rotate along the circumference. So why do you think only this marks formed and it did not?
It happens
Uh,
temperature.
mm,
So when
mm, no, not the temperature part. Again, try to think. What can you see on the left side figure? What is sort of strange? Are the ball marks there in the middle or on the side?
Sir, ball bearing only take load in the like the rotational part. Like the ball, we have to use a different kind of bearing for different loads. Uh,
No,
so
but still, whatever the reason is, when the bearing rotates, means when the shaft rotates, or one of the raceways rotates, the balls are moving along the circumference. If it is an issue with the loading caused during the movement, then you should form a continuous groove. You cannot
Sir,
form sort of
sir,
impression.
it can be due to some irregularity on the surface of the bearing.
No, Baba, the bearings are normally they go through a lot of quality checks, and manufacturing process is such that you cannot have irregularities and stuff.
Sir, it
Sir,
must have
is it because
happened
of the
when the
bending?
vehicle is stationary.
Yeah,
It
exactly.
could be
Whenever
it
the
could be
vehicle is,
it could be one or two things. So first thing is that there is a high possibility that this happened during mounting. Okay, that it was improperly mounted and instead means some misalignment and all that, because of which the rollers were actually on the side instead of being in the middle. And also during installation, if you apply large load, somebody takes a hammer and a chisel and then starts to push the bearing on the shaft, then this sort of a thing can happen. So during installation, the bearing is not rotating actually. That is one possibility. Second possibility is that someone pointed out that when the vehicle is not moving per se, so let us say it is going over a speed bump or something, and the suspension is bad and there is a jerky load which led to this sort of impressions. So these could be some causes of the indentations. Anyone else would like, so anytime you look at a failure, you have to look at it always from two angles. One is from loading perspective. How is it being loaded? What are the stresses within the system? That is one thing. Second angle is from the material perspective. Okay, only when the stresses exceed the material strength, there is a failure. So either the loading is excessive, or what else can happen, or the heat treatment was not proper, because of which the hardness of this raceway is not up to the mark and there is a failure. So it could either be because of some mounting issue or excessive loading, particularly when the bearing was stationary, or it could also be because of some heat treatment problem. But if this is a heat treatment problem, there is one more thing. Maybe none of you have visited a bearing plant. The thing is that you don't heat treat one bearing at a time. You heat treat a lot of bearings in one go. Okay, many times several hundreds of them in one go. So if at all there is a heat treatment problem, it will not be limited to one bearing. It will be extending to the whole lot. So you will have many such failures. If it is a one-off failure happening, then it is most likely from the excess loading. Okay. Next, let us move on to another application. See, in olden days, okay, so let us go back to about 150 years odd back. Now, mm, particularly in the West, okay, in US, for example, the pipes used to be made of lead. Okay, why do you think they used lead pipes instead of let us say steel or plastic?
Because of the temperature conditions.
No, steel would be much stronger.
So there were
Okay.
not many advancements in manufacturing processes of steel and plastic at that time.
Plastic 150 years back, plastic did not appear really for making these kind of commercial products. Plastic is a recent invention. Okay, so plastic is out of the question. And lead was being used for the simple reason that lead has a lower melting point and is an easy to process material. Okay, so fine, they were using lead in order to make the pipes. And what was happening was that over a period of time, so let us say in this case, this picture was taken 75 years after the installation. The pipes which were originally straight were sagging. Okay, so you can see the curvature over here. The pipes were sagging. So, what caused the sagging, and why did it take so much of time for the sagging to take place? What is the failure mechanism here?
So
So
expansion and contraction
is it
of the lead metal
No,
throughout
Baba.
the time of 75.
Expansion, contraction. Why will it result in permanent deformation, and why does it take so much time? If it is
Like
seasonal,
creep deformation.
it is because of creep deformation. Okay, so why creep is particularly a problem with lead but will not be a problem with steel?
because it is heavy
Low
to
melting
it?
point.
Because it is low melting point material. So room temperature for lead, what will be the room temperature in Kelvin divided by melting point of lead in Kelvin? What will be that ratio? Can you look up and tell me? So room temperature, let's say, is 300 Kelvin. Okay, divide 300 with melting point of lead in Kelvin. What is that ratio?
Uh,
Around 2, sir.
0.5.
No, 0.
It is 0.5. Okay, so I told you that creep starts to appear at about 0.35 times melting point in Kelvin. So it is way higher than 0.35. So it undergoes creep. Creep is a very, means depending on the temperature, creep can take a lot of time to happen. Now, but even for creep to happen, there has to be some stress within the material. What is causing the stress? What is causing the stress?
The
So it's
pressure of
because of
whatever
its
it is
weight.
carrying.
So it's high weight.
Because of dead weight itself. Okay, there is no other external loading. It is just the dead weight which is causing the loading. Okay, lead itself would be very heavy. So creep is a problem when the material is subjected to elevated temperatures and is also being subjected to loading. Okay, can you think of some other applications, engineering applications, where creep would be very relevant? Think of applications where basically parts run hot and where change in shape is a big concern.
Engine.
Sir, in boilers of power plants.
Very good. Boilers, thermal power plants are a good candidate, and boilers particularly, yes. So steel is subjected to many times above 300 degrees Celsius. You cross this limit. Where exactly in boilers do you think this will be a concern? Would it be the boiler body? Because a small change in shape in the body does no harm. So, where exactly do you think within the boiler would this be of concern? So, this
The
would
heat
be of,
exchangers.
no, heat exchanger also no. It would be of concern wherever you are using bolts or rivets to clamp things together. So let us say the boiler has two parts. which are being clamped together using bolts. Okay, and the bolts are initially being tightened to ensure that these two parts press against one another and that there is no separation between the two. But then over a period of time, the bolts can actually elongate because they are under stress now. You are compressing the plates and bolts will be in tension. Okay, so the bolts can extend in length, thereby releasing the means force which we had initially generated. Okay, that is of great concern. Somebody said engines. Which engines are you referring to?
IC engines.
IC engines are not much of a concern. Like
turbine blades basically.
turbine blades. Okay, jet engines. So if you take any of the aeroplanes, okay, if you take the jet engines, now in the jet engines, turbojet engines, so what do you have? You do this fuel combustion and then all these hot gases flow across these turbine blades. The operating temperatures over there can be around 1000 degrees Celsius. Okay, and the gap between the rotating blades and the outer body would be very very little. Why do you want the gap between the blades and the outer cover to be small?
So that as much air passes through the turbines as possible.
You want the air to pass through the blades. If it just passes from the top, then basically you achieve nothing. Your efficiency drops considerably. So you have to maintain very small gap. Now, in this scenario, when the blades are rotating, what is stressing the blade? What is causing internal stress?
So the air resistance.
Air pressure is there, that is one loading, but that is a small part of loading. There is something else which is like causing enormous
Heating,
stress.
heating of the blades.
Thermal stresses to some extent, again not too much. There is something else.
Sir, the
All rotate.
rotating of the blades.
What will that do?
Centrifugal
The
force.
centrifugal
The
force will
centrifugal
stretch the.
force. Okay, so there will be a large compression, sorry, tension, which will be generated within the blade as it is rotating at high speeds. Okay, these centrifugal forces, what will they do to the blades? What kind of a shape change will they cause?
Elongation of the blades.
They will cause
Elongate.
them to elongate along the radial direction. Okay, and this is a problem because then the blades will rub against the outer body where you are maintaining tight tolerances. So the turbine blades are one application where you are really concerned about creep. Okay, and in this power plants, all power plants, so particularly if you take these nuclear power plants now, and that too if you take these thorium reactors, I don't know how many of you have heard or read about it. Over there they use they're planning to use liquid sodium in order to do the heat exchange, so the operating temperatures are high. Basically, wherever operating temperatures are high, you have to pay particular attention to creep. Now, for plastic parts, even room temperature, you have to pay a lot of attention. Why is that so?
Low melting point of plastic.
If you are using thermoplastics, they have their melting point at about 150 to 200 degrees Celsius. Okay, so room temperature will be about 0.55 to zero point 0.6 of melting point in Kelvin. So for plastic parts, the shape change is a real concern even at room temperature. So creep is something that you have to keep at the back of your head. You need to find out what is your operating temperature vis-a-vis its melting point in Kelvin, and based on that you have to decide whether you want to concern about long-term effects or not. Okay, all right, next let us look at this study over here. So there was this factory where they were making gears for transmission systems. Okay, and what they found was that during heat treatment process, okay, so after all the machining is done, before they do a finishing grinding operation, they take the gears to above the austenizing temperature in a furnace, keep it at that austenizing temperature for some time, and then they put the gears in a oil bath. Okay, they do not put it in a water bath, they put it in a oil bath. And this is the rapid cooling which happens once you put these gears into the oil bath is supposed to harden the gears. Okay, but in one particular batch what they found was that when they put the gear into the oil bath, there was extensive cracking. Okay, so you can see these cracks, this over here, over here. Okay, you can see the cracks. They found extensive cracking. So this is from the side and this is along the teeth face. Okay, now what do you think would have gone wrong over here?
So the cutting forces might have caused some residual stresses.
Possibility, that's a possibility, but hmm.
So the cooling rates at different parts of the tooth would be different, so that would could result in cracking.
um, Again, so okay, just before you answer, maybe we'll go through these steps. Okay, so in gear manufacturing, so you first take some appropriate gear material. Okay, so typically you can go with either some high carbon steels or 4000 series steels. You do the machining of the gear teeth. So let's say you do a hobbing operation, and then you do hardening. So one is furnace hardening, or another is if it is a large gear, then you can do induction hardening of one teeth after another. And then you, so if you are doing induction hardening, then it can do self quenching. If you are doing furnace hardening, sorry, if you are doing furnace based hardening, so then you take it out and then put it in an oil bath in order to harden the material, and then after that you do grinding inspection. So these are the steps involved. Okay, so let us sort of look at what happened in this application. So first thing is that the cracks appeared on most of the teeth. Okay, then their points of origin are different for different teeth. It is not like they're all cracking from the same location. Next, you see that the cracks are running deep. Okay, so it is starting from here, coming until here. Then the cracks have smooth profiles. They are not excessively branching, oscillatory in nature, and all that. And they appeared during heat treatment process. Okay. So somebody is on unmuted. Please mute your mic always, unless you are answering a question. There is some background noise coming. So these are the observations. Okay. So right. So now you can try to think and
So,
answer. Uh,
so maybe the heating went too long and the whole of the gear was heated to a
this
high
is a further
temperature.
heating process only. Yeah, because otherwise they could have stopped after they start. They saw cracks on one of the teeth.
Oh, this went in the heating itself.
No, no, no. In heating, it won't happen. No. Yeah, during the heating process, material becomes very ductile. It flows nicely. Even if you hit it with a hammer, it flows. So there is
Yes,
no
sir.
problem.
I thought the inner would also be heated to a great
Yes.
extent, and then after it
The
went through
inner would
quenching.
also be heated, but where would the cooling be fastest when you put it in an oil bath? On the inner or on the teeth?
Or the surface.
On the outer surface. The cooling would be fastest on the outer surface. And where do you think the stresses would generate be, means stresses generated would be highest? This in this case, what causes the stress within the material during the cooling process?
So the outer tries to shrink, but the inner is still hot, so it causes stress.
Yes. So basically, the outer is cooling. It wants to shrink, but the inner doesn't allow it to shrink. Okay. So the thermal gradients are the ones which cause the stresses. Okay. So these are all thermal stresses which are getting generated within the material. So as I said, whenever you're looking at failure, okay. First point, what what do we call this failure? We don't say cracking, means
Quench cracking.
That's what I'm saying. We don't say cracking. What you see are cracks, but the failure we use another word. How would you describe this failure? It is fracture. And what kind of a fracture is it? Is it brittle fracture or ductile fracture?
Brittle fracture.
It is a brittle fracture. So the failure mechanism here is brittle fracture. Now, whenever you have a failure, I said you have to look at it from two angles. One, from what is causing the failure, the stresses, what is stressing the material, and second is from material strength perspective. So what happened over here? For something to fracture, what needs to be true? So one is the fracture strength of the material must have come down. Okay. So one of the measures of fracture strength is critical stress intensity factor. We'll look at it later. That must have come down. Otherwise, steel cracking like this is very rare. Means you abuse steel in day-to-day life like anything really. You must have all seen gas cylinders, right? You have this compressed okay, natural gas inside gas cylinders that is damn explosive. And how are they handled? Have you ever seen them unloading the gas cylinders from a truck? How many of you have seen it? Raise your hand if you have seen it. So okay, so at least a good number of you have seen it. So how do they handle it? Do they handle it delicately, as if it's an explosive, and if they touch it a little hard, it is going to fracture or it is going to explode? How do they handle it?
They
So
keep
very
throwing it
roughly,
here and
sir.
there.
Okay, they abuse it massively. They take this 30-40 kg mass and they just drop it from 2-3 meters height onto stones or bad surface or anything like that. And how is the surface of gas cylinders? Most of the gas cylinders you get in your house, is it like a perfect cylinder, nice smooth surface, or is it all dented? How is the surface of a gas cylinder?
Dented, sir.
It's massively dented, most of it. So what does it mean? It was abused like anything to have dented such a thick steel. Okay, so steel, what is their confidence? Their confidence is it will never crack. Whatever they do, it will never crack. So steel, which is normally so tough, whose fracture toughness is so high, somehow it dropped massively over here for it to fracture like this. So fracture strength went down. What could have caused that? What can cause fracture strength of steel to drop so rapidly, so badly? You have taken material science course, no? So in that you must have read about these transformation diagrams. Depending on the cooling rates, material can end up with different microstructures,
So
right?
due to irregular phase transformation within the steel.
It's not that irregular either. Cracking is happening on all the teeth.
But sir, the cooling rate is different for different parts of the gear as we.
There could be some difference, but what kind of a microstructure might have resulted in the gear for it to become too brittle?
Bainite.
Martensite.
Martin.
There could have been a very big martensitic transformation within the gear. Bainite is also quite tough actually, but martensite is very brittle. So if a lot of the gear teeth had transformed into martensite, okay, and they did not do any tempering, lot of it had transformed into martensite, then if you are so sudden cooling resulting in martensite formation and large stresses within the material can cause this cracking. Okay, so thermal gradients are one cause for the stresses. Is there any other cause, particularly during heat treatment, for stresses within the material? What sort of a volume change happens in the material during transformation to martensite? Whenever you have phase change, one thing you can pay attention to is how the specific volume of the material is changing. Okay, so Martensite formation leads to nearly 4% increase in volume, specific volume of the material, and that can also be a cause for stresses within the material. But nonetheless, the short answer is excessive cooling rate could have caused this martensite formation, which is very brittle and also resulted in thermal stresses and transformation stresses which are too high for the material, leading to such sort of a cracking. Okay, and initially I had said that they use oil quenching rather than water quenching. Why do you think that is the case? Why do you think people would go with oil quenching?
Maybe oil has a higher point of vaporization.
Okay. Actually, water quenching can be very violent. Water boils at a lower temperature, and yeah, so because of that, it can lead to very non-uniform cooling, very rapid cooling, which is a problem. On the other hand, if you use oil cooling, it's much more uniform, and the cooling rates are slightly lower, which is good in terms of reducing the thermal stresses. All right, let's move to the next story. Okay, so during the Second World War, um, well, battle was taking place on land, it was taking place in the air, and it was also taking place in the sea, in the ocean. Now, in the ocean, so the main fight was taking place between Germany and Britain, and the German U-boats were basically sinking the British ships at a fast rate. Now, in any battle, one of the very important thing is to keep your supplies intact. So wherever your army is fighting, you have to ensure that they're well fed, they have enough weapons, enough ammunition, whatever they need is being supplied. So supplies are very, very important, and also you have movement of personnel, people who are going into the battle, people who are injured and coming back for whatever reason. So you have this movement of people, and at that time anyhow major transport between Britain and Europe was through ships. Now so they needed a lot of ships. Now so at that time initially US was not participating in the war, but they were requested for making ships and giving it to UK. Their friendship has been there around for a very long time. So fine. So US started means in their shipyards. In their they started making these ships in big numbers. So and these ships they were called Liberty ships. Okay, so ships being sent to liberate Europe. Now, until that point of time, when they were making ships, they used to make the hulls by riveting thick plates of steel. Okay, so same concept. You would make a hull. You would make this internal structure on top of which you would have these plates which are being riveted together. Okay, riveting was very popular up until some 50-60 years back. Now, but then riveting was taking a lot of time. I don't know. Have you ever seen thick steel plates being riveted? Some olden time videos. So basically, what they would do is fine. You would have these two plates with some matching holes made, and then you take these iron rods. You would heat them until they are red hot, and then you would throw them from the point where you are heating it to the point where it has to be riveted. People carry it in some small bucket kind of a thing, and then someone holds it with a tong, puts it inside the holes, and then they would hammer it, okay, from both sides, such that you get this bulb or a round dimple kind of a thing which forms on both sides. And then as the rivet cools from about 1000 degrees Celsius to room temperature, it compresses, and in the process it is going to compress the two plates and hold them together very nicely. Okay, so they used to do this thing. It needed a lot of synchrony and workmanship from the people who would do it. But as you can imagine, for a big structure like a ship, it would mean enormous number of rivets would have to be sort of made, and then they have to be put together, and it was a time taking process. They could not make the ships at the speed that UK wanted. So then what they did was to increase the speed of manufacturing. They started to weld. Okay, they started to weld the plates, and then they went from a riveted outer thing to a welded structure. Okay, the outer structure was now a single piece welded structure. Now, one of the things which happens during something like a war is that your demand is very high. That means you have to make a lot of these ships. They had to make a lot of these ships in a very short period of time. So then what would happen? So you cannot just work with your normal employees. You have to employ a lot of people too. Okay. So they recruited an enormous number of welders, and they started to weld these structures to make the ships. But then once you employ people who haven't been trained properly, your workmanship goes down. So anyhow, they made all these welded ships, and then these ships were to sail in the North Atlantic waters. So now one of the things about the North Atlantic waters is that the waters can get very cold. So you can have temperatures even drop sub-zero inside the water. So the temperatures can be very low. And what they found was that these ships, in some cases, they would just crack, means they would crack extensively. And in three of the ships, basically the ship broke into two pieces, okay, down the middle, and massive accidents. So now the thing is, it never happened before. So why do you think this welded structured ship would break? And what do you think is the relevance of this North Atlantic water? Why so specific that the failure should happen in these waters?
So it was fatigue failure.
No, fatigue is repeated loading over a period of time, and fatigue failures normally they would not be catastrophic. They would slowly progress and then lead to final failure.
So maybe it is due to
So the
corrosion failure.
temperature of the North Atlantic waters is quite low, and
So
like specifically
levels of
the
temperature for metals, like you take aeroplanes. Aeroplanes are flying in air, and when they are 10 kilometers above the Earth's surface, the temperature over there can get to minus 20 degrees C and all that. So if nothing is happening to the aeroplanes structures, why like this particular thing has to rupture even at 0 degrees Celsius?
So the
So
material
can
was.
this because of overloading of the ship maybe?
No, the ship is designed for some load. So normally, now what I have seen is this stress not exceeding yield strength is a thing which people have been following for a very long time now. And also remember that this is not the first time they were making this ship. They have been making it for a very long time. And in any case, the structure, as I told you, so
sir,
Sir, due to weld
the
stresses, the
the
because
only change you mentioned.
previously
Yeah.
we were riveting, now we are using weld. So due to the cooling, the contraction might not be proper and stresses might have developed.
that could be a reason that welding is causing some sort of cracks. But why would they not fail immediately? Why would they take so much of time to fail? And that too when they sail in this North Atlantic waters.
So there might
Again,
be
the
some
So
phase
we
change
microstructure can
happening.
change. Phase
Sorry?
change happening in the colder waters.
So there are two, 3 points over here. Anyone else would like to venture? You guys are
because
close.
salty.
Maybe because the
Because
ship
salt.
is welded, so even if a small crack is obtained in the metal, though it will like
No, but
um,
defects are there always. Now you can never make a part without any defect. That too
So,
when you're making such large structures.
so that the
sir,
small cracks will propagate without any obstruction. So if we like irrespective of the if the hull is made out of riveted steel, the cracks will obviously propagate without any obstruction in a welded like a continuous steel.
That is a very good point, and that was one of the causes for this catastrophic failure. But please remember, I told you 2-3 times that you should always look at the problem from loading perspective and material perspective. Somehow the stresses are higher and the material strength is dropping. So, what is causing the drop in strength of the material?
Sir, maybe
Sir,
due
like
to lowering of temperature, the ductility of the ship is reduced.
There is a specific, this is a specific problem for body centered cubic metals like steels. What is this thing called?
embrittlement, sir.
No, this is called ductile to brittle transition. Okay,
Yes, sir.
you must have heard this term before. The ductile to brittle transition is a big problem for body centered cubic metals like steels, and for today's quality of steels, this ductile to brittle transition is sub zero. It is well below zero, maybe -10 -20 degrees Celsius. But at the time of the Second World War, the quality of steel was not so high, and the ductile to brittle transition was somewhere around that zero or slightly higher than zero. So when they went sub zero, the embrittle, I mean, the material had become quite brittle. There was a very sharp drop in the fracture strength of the critical stress intensity factor of the material. So that was one thing. The second thing was that it is an all welded structure. So once the crack forms and starts to propagate, there is nothing to stop it. If it is riveted, it stops at one of the rivets or at the plate. Okay, but this one it can run continuously. And third problem was that the quality of weld was not up to the mark because, well, the not all workmen were of high quality. So because of all these reasons, they had extensive failures in these Liberty ships, and some of them had actually broken in half, either in service or as soon as they were taken out of the yard. Okay, next, let me move on to another story, and this,
Sir,
yeah.
sir, but why only three ships like face this situation instead of all those 2,700?
Good point. So failure is not uniform normally. So it could have happened that no, in many of the other ships there were problems, but it did not break into two. There were extensive fractures, but they did not catastrophically break into two. Why failure happens only in some and not in all the things? Many a times it can be a combination of many things. One is maybe in these ones the defects were much more as compared to the other ships. Maybe these ships ran into rough waters, so you go into a sea, and if the weather is bad, they can be extensively loaded. Okay, so it would be, the simple answer is not all ships are the same. Microscopically or locally, the defects are different in each one. Not all of them would be subjected to the same set of conditions. Mainly in the case of ships, the weather based loading would be different for each of them. So a combination of factors. And another thing could be that if you spot a failure beforehand and if you fix it, there is a chance that you will not have a catastrophic failure. So, all right, let me move on to the next case study. So in the early 19th century, so we are talking about 1800s. So when the British Army was in India, they used to use these brass cartridges in their guns. Now so what is shown over here are the case of these cartridges. Now within these cartridges, they would store the explosive powder, and this would come as a two-piece thing. Okay, so one would go on top of another, and this brass cartridge used to be made using cold forming technique. Okay, so at room temperature they would have some forming press where they would make this brass cartridges, As you can see, it is not a high quality forming operation. There is a lot of wrinkling which is there on the cartridge. Now they used to store all their ammunition in these horse stables. Okay, and then what they were finding was that particularly in summer, okay, these cartridges used to crack. Okay, they would crack open like this. What do you think is happening? Like there is a relevance of what are the keywords here? They have made them using cold forming. Uh,
Residual stress?
yes, the cold forming results in residual stresses. Very good. So you have residual stresses. Then these were being stored in horse stables. So there is some relevance of that. And then the problem was severe in summer. Okay. How many of, can you please raise your hand if you have been around some shed or around animals? Particularly if some of your family members rear animals, or you have visited cowshed to collect some milk, or just have you been around animals? Raise your hand if you have been. Arey Baba, so many of you have not been around animals for 20 years. Okay, fine. So you have been. So if you close your eyes, so like, what are the feelings that come back to you? Like, what captures, what strikes your senses when you are inside a cow shed, or for that matter a chicken shed, or any
The
animal?
smell?
Smell.
Smells.
Okay, it's very strong. The smell is very strong. Okay, so they do number one, they do number two. It's not cleaned regularly, and anyhow, they are not as spotless as your bathrooms. So fine, there is smell. There is strong smell. What is the smell of? Like, what is the chemical? What are you smelling?
Methane.
Methane?
You are smelling methane, or you are smelling ammonia. Most of the time, the smell is from urine. So you are smelling ammonia. Okay, fine, all right. So there is this smell which comes. Like, what is the role of the season? This used to be called seasonal cracking because it used to happen in summer most of the time. What is the role of the climate? Why do you think in summer things would be bad?
Maybe more
So
humidity.
Huh?
the sunlight
Humidity.
somehow
No, reverse. No,
decompose
summer humidity levels are lower. Huh?
uh, does the sunlight somehow like decompose ammonia and the
Most
resultant
of the time
nitrogen
inside the
attacks?
shade there is no direct sunlight in the first place, and in any case exposure to sun harms nothing really. There is a few degrees increase in temperature, and that doesn't lead to cracking. So what do you think would be different in summer?
Maybe the reaction rate of ammonia with the metal.
No, it's
The
little bit. You're talking about diffusion of ammonia.
Hmm.
So the ammonia will be more volatile in summer season, so it will diffuse more.
Very good. That is the point. So basically, so means you take, if you take urine, it has a boiling point, right? Means the ammonia is coming out of urine. Means these liquids have a low boiling point, and in summer the amount of ammonia which is released is much higher than it is in winter. And what this ammonia is doing is it is going into the metal. Okay, it diffuses into the metal and it embrittles it. It basically drops its strength. Its critical stress intensity factor goes down, and as it goes down, at some point the residual stresses are strong enough to crack open wherever you have large stress and some earlier defects. And particularly this wrinkling was creating the stress intensity factors. and at those points it would start to crack open. So even though this was colloquially called seasonal cracking, this kind of a failure is called stress corrosion cracking. Corrosion is leading to reduction in the stress intensity factor or the strength of the material, and the residual stresses are basically cracking it open. This is called stress corrosion cracking. This is a similar situation. So like in US, they use this steel pipelines, more specifically stainless steel pipelines, for transporting for transporting. In this case, they were using it to transport carbon dioxide feedstock. Okay, so maybe for some chemical industry, and this pipeline was buried 4 feet below the earth. Okay, and so in US they have this problem of snow during winter, and to remove the snow they add salt. Why will salt help you remove the snow?
It reduces the freezing point of water.
Very good. It reduces the freezing point of water. Okay. So let's say the temperature is -2 degrees Celsius, and when you add salt, the freezing point goes to -4 or even lower. So it melts. So they use this salt to de-ice during the winter months, and the pipes, they would notice that over a period of time they would generate cracks like this. Okay, so you see this branching kind of cracks in the pipes. So what do you think is happening? This is an example of stress corrosion cracking, but the ice on the salt on the road, how is it reaching the pipes?
So the
So
melted
the
water percolates through the
yeah,
soil.
So the basically salt dissolves in water, and it seeps in through the soil, comes to the pipes, and it is corroding the pipes. Now, as I told you, you need to have two things in play for cracking to happen. So one is this business of reduction in strength of the material, and second is internal stresses. What could be causing the stresses in the pipes?
The
The
gases which are
stress
flowing.
from the gas.
Uh, Stress from the gas may not be that much. It could be a reason, but not much.
So due to the temperature gradient.
No, Baba. Temperature gradients normally do not cause that much of a. How much gradient will be there? Do you think in the pipe at two locations you would have a big difference in temperature?
So the inside liquid flowing in the pipe can be of different
Gas, carbon
temperature.
dioxide gas. What gradient can it create?
The weight of the soil above it.
No. There is soil below also, no? There is some amount. It's mainly
Sir,
residual stress
pressure gradient.
created during manufacturing itself. One means we tend to think that only external loading causes stresses within the material. Many a times the manufacturing process itself creates a large amount of stress within the material. So if you do any sort of a welding operation, or if you do any cold forming operation, it results in very large amount of stresses within the material, which far exceeds anything that you generate through external loading. Okay, so these internal stresses can means result in this stress corrosion cracking. Okay, I think I'll try to finish in another 10 minutes. So all right. So in one particular application, they were using a axial flow fan. Okay, what do you mean by an axial flow? What do you mean by an axial fan? We say centrifugal pump, axial fan. Axial fan means nothing. The pressure gradient is being created along the axis of the fan, and flow is along the axis of the fan. Okay, so there was one application where it was observed that all blades of a fan failed after 100 hours of operation. Okay, and then they started to blame each other, as it happens in any company, as to who is responsible for such a bad design of the fan. And they thought that basically somebody forgot a spanner or something, and then over a period of time one blade got damaged and it led to damaging of other blades. So after some days they replaced the fan with another fan, and the second fan also failed exactly after similar number of hours, like about 100 hours of operation. Again all the blades broke. What do you think was happening in this application?
So the the blades
What
got
type of failure
expanded.
is it?
So due to plastic deformation of the blades.
Why did it take so much
Due to
time?
heat
Why
generation,
100 hours?
due to heat generation from the.
So it could be a
No,
fatigue failure.
not that much. Huh? How much? What fatigue? It
Fatigue.
is fatigue failure. Okay, anytime you have a failure after repeated use, it's fatigue failure. Fine. So it is fatigue. So, but then fatigue is normally unpredictable. Like you don't know where it is going to happen. It may happen, it may not happen, and it doesn't always happen after same number of cycles. So what is happening? It is fatigue, but it's a special kind of fatigue failure. And fan normally the loading is not so very high, and anyhow you take care of all those things when you're designing the blade. So what do you think went wrong? Why do you think the loading became too much higher than what it was supposed to be?
Sir, due to some unchecked vibration, maybe.
You're close.
So they missed out a part, maybe some sort of a bearing.
No, 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 no. Again, see, remember that in case you do a bad assembly or you forget some part, as soon as you switch on, there must be like, you should immediately figure out that something is wrong. Means it doesn't take a genius to know that you have forgotten a bearing, and you cannot forget a bearing in a assembly like this. But you should figure it out immediately.
The misalignment of the axis.
How many times will you misalign? It happened again the same second time, and why so much time? So, one of the things that you have to keep in mind, anytime you have a dynamic system, you have a motor, an internal combustion engine, and parts are moving, okay? One of the things you have to be really careful about is resonance, okay? Whatever is your driving frequency, so over here as the blade rotates there will be some vortices which will be created, which are going to vibrate the blades, and the frequency of this vibe means external forcing will depend on the rpm of the blade. Okay, now in this particular case what was happening was, the speed at which they were operating, there was a resonance in the system. What does resonance do to the loading which happens on the blades? What happens in resonance?
So the amplitude of vibration goes up successively.
Amplitude of vibration increases tremendously. Okay, particularly if it is an all metal structure, it doesn't have much damping, and amplitude of vibration will be much higher, maybe 5 times, 10 times of that of the normal loading. So what will happen? So what is the harm? Let it vibrate, let the amplitude be high. So what is the problem?
So, but the strains will be too much if the amplitude goes unchecked.
But it's not just that shape vibration which is a problem here. Noise is an issue, but the another major concern is as it vibrates so much, the strains and the corresponding stresses will be very high. Now, what happens if the stress exceeds the yield strength of the material? Why is it not just undergoing some shape change, simple bent shape change? Why is it breaking?
So once it overcomes the yield strength, there will be plastic deformation, and so the fan blade could get stuck. And
Well, let it bend a little, let it deform a little. Why is it breaking?
Because, sir, it is rotating
Airflow
at
is then not uniform, so
Because it is a vibration system. It is not getting loaded monotonically in one direction. Okay, so it is not just plastic yielding in one direction. It will be like compression, tension, compression, tension. It is being cyclically loaded, and it is experiencing a special condition which results in something called low cycle fatigue. Okay, it is fatigue failure, but in each cycle there is a plastic deformation also, and it is this accumulation of plastic deformation which is leading to failure. And because it is low cycle fatigue is predictable. High cycle fatigue is highly stochastic. You don't know when it will happen, but low cycle fatigue can be predicted. And because of this, all baits were failing exactly after same amount of time, and this happened in both the cases. And a simple solution to this, what is a simple solution to fix the problem?
Yeah, damping.
Change some diameter or some
You
dimension.
can't add damping. You can't do any major design changes. It will take a lot of time.
Reduce the speed of the fan.
But that's it.
Just change the
Move
frequency of
away from
operation.
the speed at which you are having this. Move away from the speed at which you are having the resonance. Okay, you can either operate at a lower speed, slightly lower speed, or you can operate it at a higher speed. If you operate it at a higher speed, you will still have to cross the resonance speed. Na? So what will happen?
The fan's blade might
It
touch
will
the.
have resonance, but for a very short period of time, because you're not put at that speed. You must have noticed this whenever you are driving a car or many appliances. You will see that at some particular speed there is more amount of shaking or vibration, and then once you cross that speed, you are feeling much better. Okay, so they just moved away from the resonance speed to prevent the failure. Okay. Okay, last one, two things I have. I'll move faster now. So this is a rail fracture surface. I just need you to. So many times you have rail accidents, and they keep blaming the rail fracture for that. You can see two distinct regions here. So one is this region. You see these marks over here. What these patterns? What do they remind you of?
Ripples on a water surface.
Yeah, ripples on a water surface. Anything else?
Tree
Seashells.
trunk.
Huh?
Tree trunk.
Tree trunk. Okay.
Seashells.
You can also see these kind of ripples on a sand surface. Okay. In a desert, on a beach. So these are called beach marks. Colloquially, these are called beach marks. And what do you think happened here? So there was a small defect here, and the crack surface slowly started to propagate over a period of time due to fatigue. Okay, so up till this point, the crack increased in size from fatigue, and beyond this point, there was a catastrophic failure. So the remaining surface is a brittle fracture. So this is the typical failure mode. So when the crack is small, initially it propagates from fatigue. That happens over a period of time. Once it reaches a critical size, then there will be catastrophic failure. You have to detect the crack well before that. Last failure mechanism is wear. Okay, so if you take railway wheels, normally after every 100 200,000 kilometers of operation, their profile will change a little bit because of wear and tear. Okay, so material gets worn out. So between the wheel and the rail, which do you think should be made harder? One of them is slightly harder than the other. Which one do you think would be harder, the wheel or the rail?
The
The
rail.
rail, sir.
The rail.
They would be harder. Why do you think they would make rail a bit harder as compared to the wheel?
So it's easier to remachine the wheel than the rail.
Very good point. Okay, so replacing rails is a very difficult affair. So because of that, they make the rail a bit harder, not too much, a bit harder as compared to the wheel. So wear and tear is another issue that you have to be concerned about. Now in this course, we are going to lay down particular emphasis. We will study a little bit about the deflections part, a little bit about buckling, but we are going to pay a lot of attention to plastic yielding, failure from plastic yielding, a little bit on brittle fracture, and a lot on fatigue, fatigue-based failure. Okay, so these are the mechanisms we are going to focus on in this course for all the machine elements. Okay, all right. Now I am going to copy a link onto the chat box. Okay.
Just a minute.
Yeah.
I wanted to ask in the second last, in the benchmark failure, what is the failure mode called?
Sorry, what is it?
Mode of failure in the failure of rail.
Failure of rail. It is fatigue followed by fracture. Yeah, just a second. All right, so I'm stopping the share. Now, please go to your chat box. I have pasted a Microsoft form. Fill this up. Okay, so you have 10 minutes to do it before the end of class. So please do it.
Sir, it is not accepting responses.
It is not accepting responses. Okay, just a second.
Yes, sir. It is not accepting it.
Okay, just give me a minute. I'll change it.
So you can stop the recording now.
Yes, thank you.